attempts to apply some of the lessons from naturalized metaphysics, so using that methodology to investigate what we can learn about metaphysics from a careful study of some situations in physics. So it's a pretty good thing. And what we hope to get from this is some comments on metaphysics itself, so the content of metaphysics, and in particular, today we're focusing on the principle of separability. So that's a metaphysical principle, and we're going to investigate whether this principle should be revised in light of sort of developments in 20th century physics. The second part of it, we're also going to comment on some sort of metaphysics. So through looking at physics, through looking at the way that this principle of separability gets revised, we want to then feed back into the methodology of naturalized metaphysics to decide if we want to update that methodology at all. And in particular, we're looking at the principle of naturalistic closure and the role of intuition in the development of physics. So we've got two kind of lessons that we're taking from physics, about metaphysics itself and about how we do metaphysics.
Arrow maybe? Oh, okay, yeah, just click on that.
Okay.
There, so we're down.
So just to get started, we've got two possible aims of metaphysics, which hopefully combine, but there's perhaps some tension between them. So one possible aim of metaphysics is to model the objective structure of physical reality. A different possible aim of metaphysics is to develop principles, conceptual principles that help with the development of empirically successful, useful physics. So we've got the first aim of metaphysics is investigating reality. The other one is producing physics, which is useful for us. So we've got a metaphysical aim, or more traditionally metaphysical aim, and a more practical aim of the subject, the discipline of metaphysics. So to get some more teeth into this, we're going to use naturalized metaphysics as it's kind of articulated by Ladyman and Ross in their 2007 book. I'm sure many of you here will be familiar with Everything Must Go. So taking from that three central features of the proposal of naturalized metaphysics, we've got a negative view of the role of intuition, in particular everyday or common sense intuitions. These are seen to play no role or no helpful role in the development of physics, and intuitions are supposed to be absent from metaphysics. They don't help with the aims of metaphysics, according to Ladyman and Ross. The second feature is the principle of naturalistic closure, which I'll go into in more detail in a second, and the primacy of physics constraint. The third of these is kind of running in the background, so I will go into a little bit more detail about it, but it's the first two really that we're going to be focusing on with our kind of metaphysical studies. So on intuition, we have this statement that everyday or habitual intuitions and cognition are not likely to track truths reliably across all domains of inquiry. There is no reason to imagine that our habitual intuitions and inferential responses are well designed for science or for metaphysics. Okay, so a very clear negative view of intuition there. The principle of naturalistic closure is the requirement that metaphysical claims, if they are to be taken seriously, be motivated by and only by the service they would perform in unifying specific scientific hypotheses, at least one of which is drawn from fundamental physics, in order to explain more. So there's some kind of little bit of paraphrasing here, trying to condense the sort of thrust of this principle. But we've got stuff to do with the motivation behind metaphysical claims. Okay, and here we've got focus on the very pragmatic aim of metaphysics. But then this last bit about, in order to explain more, the way that sentence continues in the book is it goes on to say that what we're explaining is the structure of physical reality. So we've got the principle of naturalistic closure, involving both the pragmatic concern with developing conceptual principles that are useful, and also using those to develop physics that then explains or describes the structure of the physical world. And then the primacy of physics constraint, we'll just mention it so you can kind of have it in the back of your minds. It's the stipulation that the failure of an interpretation of special science generalizations to respect negative implications of physical theory is grounds for rejecting such generalizations. Now, everything that I'm going to talk about is to do with physical theory, so we're not too concerned with special science generalizations. But this really has to do with the scope of the kinds of metaphysical conclusions we reach based on a study of physics.
I think the arrows will work now.
Okay. So we're going to apply all of that very general machinery to the principle of separability. So it was originally kind of discussed and formalized by Einstein, as far as I'm aware, and has to do with a very practical requirement on our ability to do experiments. So in order to get clear experimental results, we would like our experimental apparatus to be isolated from the environment, at least for all practical purposes. So that the measurements that we obtain about that experiment pertain to that experiment and not something else. Okay. So it begins with a practical requirement. It's also quite intuitive. So the idea that this region of space has its own properties that are independent of this other region of space somewhere else. This has been formalized in different ways. One of the kind of quite popular ways of formalizing the principle of separability is as supervenience. So a sufficient condition, or a condition which is supposed to guarantee separability, is the supervenience of all physical properties of a composite spatial region on the physical properties of its subregions considered separately. Okay. So equivalently, for any two non-intersecting spatial regions A and B, fixing the physical properties of A and B separately is sufficient to uniquely fix the physical properties. That should be A union B, so the union of the two regions. So there are no new properties in the union of subregions that are not already present in the separate subregions. Okay, so we build properties of larger regions of space based on properties of smaller regions of space. Some authors have taken this into the limit, so rather than just looking at subregions, we're taking it into the limit where the subregions can be arbitrarily small. Okay, so this links in a way to Humean supervenience, where we've got all properties supervening on properties of points, intrinsic properties of space-time points, or spatial points for now. So a few questions about this. So we've got that supervenience is sufficient for separability in the sense of providing us with a formal condition for the mutual independence of the formally expressed properties of distinct spatial regions. But is it necessary? So do we need supervenience in order to meet the practical requirement of separability? In other words, are there other ways of ensuring a kind of practical separability that allows us to do experiments and to kind of gain knowledge from our experimental results without requiring something as strong as separability? And then the more metaphysical part, so that's a kind of practical question. The metaphysical part, we've got, do we need supervenience to be true of the physical world in order for metaphysical separability to hold? So again, querying this relationship between supervenience and separability. So does supervenience guarantee the kind of separability we require for the practical activity of physical research, or to understand the structure of physical reality? The second of those questions, we're really asking, is physical reality separable? Okay. So now we're going to get into a little bit of a physical example. where this principle of separability, which we have good reason for wanting to endorse, we've got a physical situation where there's maybe some reason to doubt it. So first of all, to doubt the metaphysical thesis of separability. And then that leads to open discussions about which sorts of separability are going to be useful for producing empirically successful physics. So I'm going to try and just really quickly run over the sort of background of the Aharonov-Bohm effect. Hopefully it's familiar to some people, so it doesn't matter that I'm kind of rushing a little bit for this part. So maybe it helps if I draw one there. So we've got some. We've got a beam of particles coming from here. And a detection screen here. So the particles go through. These are some kind of quantum particle, photons of light, if you like. In the middle, we have a solenoid. So this is kind of looking face down on the experiment. This is idealized as being infinitely long, and it's shielded from the rest of the equipment. Okay, so the particles pass around and they produce some kind of interference pattern on the screen. Okay. So in this region, outside of the solenoid, away from the solenoid, we have some particles described by a wave function. In here, we have some magnetic field. Okay. And we can turn this solenoid on or off. Okay. And when we turn it on, we get a measurable, observable shift in the interference pattern at the screen. Which is something that we would like an explanation for, simply because changing the electromagnetic field or the magnetic field in this region should not be affecting the way that the particles move. So no change happens to the magnetic field anywhere around here, yet we observe a shift in these this interference pattern created by the particles, even though they're not passing through this region. So this is well shielded. Okay.
Sorry, just a clarificatory question. When you stated the principle of separability, you said the physical properties of two regions are independent from each other.
Yeah.
But now you are introducing an intervention.
Yeah.
And this can come apart, right? The physical properties of the two regions can be interdependent, and still interventions in one, there's a separate principle that interventions in one shouldn't affect the physical properties of the other thing. It seems to me there is another level here that you're talking about interventions now, and you didn't.
Yeah, good. So this, I hadn't really thought about it in that way, but that's another kind of layer to it. So the metaphysical principle of separability should, I guess, ensure that this intervention doesn't affect this, right? So if we're finding that intervening with the magnetic field here, so you're right that we've got this kind of interventionist level, which I'm kind of just assuming follows from the metaphysics of separability.
I disagree that it does. So I think
it does. Yeah. Okay.
Yeah. So
But this is certainly for discussion. We should,
Yeah.
because it's a nice topic to discuss, but we should let her finish presenting.
Yeah. So okay. So for the purposes of this talk, I'm assuming that the metaphysical principle of separability, as I've described it so far, ensures that interventions in this separated region do not have any effect outside of it. Okay, so I'm just assuming that for now, but that's something that is good for discussion. So in any case, we want some way of explaining this. So we might explain it by saying that, well, separability fails, these regions are not distinct, or there's some kind of interdependence between them. naively, we might think of this as like a non-local effect of the magnetic field. So we change the magnetic field here. Somehow that propagates out into this region. Either it propagates out, or we just have a non-local change in the B field in this region, which is sort of inexplicable locally. I'm going to skip forward to these. So we've got three sort of physically reasonable assumptions that are going on in the background. We're discussing separability, that's the one that's being held up for question. Causal locality is what's kind of being questioned when we're thinking about do the magnetic field properties of this region have to propagate out by some process? So we change the magnetic field here and then there's a ripple effect coming out. That would be a way of ensuring causal locality. So causal locality I'm taking to be following from the constraints of special relativity, and I'm not wanting to question it. So the sort of mysterious idea that we might get an instantaneous change in the B field outside here when we change the state of the solenoid in here, without any mediating field to connect the two. For me, that just defies any sort of physical explanation. You might disagree, but for my purposes, causal locality is kind of sacrosanct. So how else might we try to explain this effect? If we look at the mathematics of electromagnetism, just classical electromagnetism, the B field is related to this A field, so the vector potential. By the way, the B field is the magnetic part of the electromagnetic field tensor. It's equal to the curl of this vector field A, which is known as the electromagnetic potential. And we can express dynamics in terms of A rather than B. And maybe we then want to, and A is defined all over this region. That's the point. So we have sort of the beginnings of an explanation of this observed shift in the interference pattern using the A field, because it's defined everywhere. So we can use the A field to restore a kind of locality to this situation. But then it's not clear what physical properties the electromagnetic potential is representing. So contrast that to the B field, the magnetic field. That's something that we can measure. We can measure easily the strength of the magnetic field, but the potential is somehow more mysterious than that. We can't put a probe in here and measure the strength of the electromagnetic potential. It's somehow mysterious, and it also has gauge freedom. So if we add to it the derivative of an arbitrary scalar field, we get something that's empirically equivalent and something that serves the same role in the dynamical equations of electromagnetism. Okay. So I haven't said much about gauge invariance. So given that it has this gauge freedom, we can apply this mathematical transformation to the A field, and the two situations are empirically equivalent. So we don't have sort of unique predictions for the value of the A field coming from the theory. So when a quantity has gauge freedom, then we kind of break this tight connection between the mathematical formalism and the empirical measurements that we're able to perform. Okay, so we would like all of our measurable observables to be gauge invariant, meaning that we want them to not have this gauge freedom. We want them to have unique values. Okay. Does that make sense to everybody, please? So motivated by this, we've got Richard Healey and David Wallace attempting to explain the Aharonov-Bohm effect by finding gauge invariant features of the system. So neither of these two philosophers attribute physical reality to the electromagnetic potential A directly, but they both use it somehow to find gauge invariant features of the system that can help to explain the effect. So for Richard Healey, this is his preferred interpretation, is using what's called holonomies. The holonomy of a closed curve C, so we can think of beam of particles, we create a closed curve in the space. The holonomy of a closed curve is the line integral around that curve of the A field. And this is a gauge invariant quantity, okay? And that can be shown mathematically, but I'm not going to go through the details. You can ask me later if you want to know details of that. So we now have then an explanation. So the idea would be, just to try and get a bit more conceptual clarity on this, the idea would be that changing the B field here also changes the A field here. And then the A field, it has these line integrals on closed curves around that kind of ripple out. The A field is not shielded in the same way that the ordinary magnetic field would be. So we have this kind of rippling effect of the line integral of the A field, then causing the shift that we observe. So supervenience in a certain way fails because a holonomy can't be uniquely fixed by properties assigned to sections of the curve. What we mean by that, the holonomy is a property of a curve in the space, right? And we can't define a holonomy for a little bit of the curve. So we're talking about subregions or holonomies of these regions, fixing those doesn't have anything to do with the holonomy assigned to the curve that we started with, that we want to investigate. Okay. So in a certain sense, if we go into this explanation of the Aharonov-Bohm effect, we end up with an ontology which is non-separable, because the properties assigned to regions enclosed by the curves don't reduce to properties of the subregions. For those of you that are kind of into the maths of this, we also have that the line integral around here is equal to the flux through the region. So we can think of it, it doesn't have to be thinking of it only in terms of lines, we can think of it as flux through a region.
But you could cut this big region into smaller regions. And then the holonomy of the total thing would be equal to the composition of all the holonomies of the small loops.
I believe that's the case if we have a simply connected region, right?
Exactly. So
in this case, we have, because of the presence of the solenoid, the region is no longer simply connected. Good. Thanks for pointing that one out. So yeah, so in general, the holonomy is thought of as the flux through the region can be decomposed into the flux through all of the subregions. Good, unless we have a hole in the region, okay, or the region split in two, something like that. So in the specific case that we're looking at of the AB effect, we have the presence of the solenoid means that the region is no longer simply connected. As long as that solenoid is infinitely long, okay? If it's only finitely long, then we can think of the region as being simply connected. So again, some tricky details going on. But yeah, the basic idea of Healey's interpretation is that we just have these holonomies which are line integrals or surface flux integrals through the region, which don't decompose in this circumstance. So a different explanation of the same effect, we've got David Wallace wanting to preserve the principle of separability. For Healey, he's quite happy to sort of give up on it. Doesn't talk too much about the negative implications of that for doing physics practically. He sort of suggests that this situation, if we can describe it well using non-separable holonomies, this indicates that our ontology can be non-separable, or even ought to be non-separable. And he advocates kind of applying these lessons to cases like entanglement in quantum mechanics. So inviting sort of non-separable explanations and kind of no longer requiring that everything reduces to, all properties reduce to properties of subregions. David Wallace wants to preserve separability. In particular, he wants to preserve separability as supervenience. So instead, he explains the effect in terms of d theta, which is the gradient of a scalar field theta minus the potential A, where this theta is the phase of the wave function describing the interaction between the wave function of the particles considered on their own and the A field considered on its own. So there are different ways of writing this down mathematically. But the point is supervenience is restored because d theta, so the covariant derivative of the wave function's phase, is defined at every point, okay, just like the A field is. So an interesting feature of this is that the physics emerges in the interaction between two fields. So the main take-home lesson that Wallace wants us to learn is that the A field on its own has no physical properties, and the particle's wave function on their own doesn't contain physical properties. What we need to do is think of the whole setup as an instance of a semi-classical field theory. So we're looking at interactions between the classical electromagnetism and quantum mechanics describing the particles. And he says that sort of most writing so far on the AB effect doesn't take sufficient account of this. The fact that we're using a quantum theory and a classical theory, we want to combine them. So when we combine them properly, Wallace says, we get this gauge invariant object, d theta, which does the explanatory work. Okay. So we've sort of gestured towards how Healey's interpretation becomes non-separable and Wallace's interpretation preserves separability. Just a little bit more sort of formal definition on that. So Healey describes weak separability as the condition that any physical process occupying space-time region R supervenes upon an assignment of qualitative intrinsic properties at space-time points in R and or in arbitrarily small neighborhoods of those points. So it's just a more precise kind of formulation of the sort of vague notion of separability that we've been using so far. So this condition fails for Healey's interpretation. The holonomies don't meet it. In particular for non-simply connected regions. So this is from what you were saying before. And then it's kind of an open question at this stage whether or not this particular failure of separability is actually a problem for experimentation. So the way that we've set it up, we've got our experiment isolated from the rest of the world. We're not saying that there's some physical properties far away from this experiment affecting what goes on in here. We're looking at different regions within the same experimental setup. So in this particular case, it looks like this failure of separability is, I want to call it a local one. It's local to the experiment that we're working on. When you want to apply the same ideas to entanglement, then we might get a different sort of problem coming out, because there we have separate experiments that need to be combined. But in the Aharonov-Bohm effect, in this case at least, it seems to be not too much of a problem for experimentation. The fact that we have some non-separability in our explanation for it. So then Wallace attempted to restore separability by explaining the effect in terms of the covariant derivative of the wave function's phase. And he demonstrates that the gauge invariant scalar field rho, so that's the magnitude of the wave function, and the vector field d theta that we've been talking about, when they're defined on separate regions, they are sufficient to uniquely fix all physical properties of the union of those regions. So separability as supervenience is that formal condition is met by Wallace's account of the AB effect. I question the extent to which this is motivated, because this formal definition of separability, so fixing everything in separate subregions, we fix rho and we fix d theta, and that's sufficient to fix rho and d theta on composite regions. That seems to be saying something metaphysical about the situation, but given that there's an alternative explanation available that doesn't meet that requirement, it's an open question still as to whether our ontology ought to be separable or not. The way that these two authors sort of write their papers in response to each other is kind of set up as like one interpretation against the other. The way that I think about it, I'm kind of looking for what we can learn metaphysically and methodologically from considering both. So I'm not too interested in which interpretation is better or which is sort of more virtuous. But we can get somewhere by sort of comparing features of them. And in fact, Wallace actually shows that there's a formal equivalence between holonomies and the covariant derivative of phase. So he recovers holonomies from d theta, and this ends up in a mathematical expression, which I haven't written down.
Just very quick. For the Wallace thing to work, for rho to be well defined, he needs the electron field to be non-zero wherever it is in the entire region.
Okay.
So it's not the rho is not defined at the electron field vanish setting point.
Okay, good. So that's kind of more detail. I'm thinking about it as a semi-classical field theory rather than a particle theory plus a field theory. Yeah. So this stream of electrons going like this, that's not a good picture. We have a quantum field defined over the whole region. Okay, and then we get physics coming out, and that quantum field must be non-zero everywhere. Good. And then we get physics coming out in the interaction between that field and the A field. Good. So he's able to recover the holonomies, Healey's holonomies, he's able to recover them from d theta. So there's this formal equivalence between them. The way that Wallace writes about it is suggesting that the d theta is more fundamental than the holonomies. And he sort of suggests that it's an advantage of his interpretation that we can recover the holonomies. So we can talk about holonomies still where it's useful, but they're not fundamental according to Wallace. Looking through this formal equivalence that he shows, or his recovery of the holonomies, what I see is equivalence rather than one being derived from the other. You can reverse the whole thing. You can recover d theta from the holonomies. So it's kind of an open choice about whether we take holonomies or the covariant derivative of phase to be fundamental. Okay, so if we take holonomies to be fundamental, then we get a failure of a formal definition of separability. if we take d theta to be fundamental, then we meet the formal condition of separability. Both interpretations rely on gauge invariant quantities. This means that they're measurable in principle, but can we measure either of them in practice? Again, this is an open question, and if anyone knows more about this than me, then please let me know. So d theta is a vector quantity that, yes, is defined at every point, but as far as I understand, there's no experiment we can perform that actually measures the value of d theta at a point. What we can do is measure the interaction wave function. We can derive d theta. Same with the holonomies, that they're measurable only indirectly via the shift in the interference pattern. That's a sort of experimental consequence of these things. So they're kind of open questions. The reason why getting clear on this in the context of a situation like the Aharonov-Bohm effect or like quantum entanglement, getting clear on the ontology of these physical theories which are well confirmed, well established, sort of fairly well settled as bona fide physics. We then want to sort of gesture towards quantum gravity or more generally open physical problems. So thinking about the practical motivation for doing metaphysics, getting a clear ontological interpretation of a past theory can help us to establish the foundational principles of the theories that are not yet settled. So big open problem in physics, as we all know, is quantum gravity. And we want some kind of guide to how to go about solving that problem. Obviously, there are many different ways of trying to solve that problem on the table. As philosophers, it would be nice if we could get a handle on those and try and comment on which research programs are kind of worthy of pursuit. So we go back to the PNC, the Principle of Naturalistic Closure, which recommends taking seriously only those parts of metaphysics that are most likely to be useful in the development of empirically successful future physics. So Michael Redhead talks about this in terms of underdetermination, where we have a underdetermination in interpretation of one established theory. We should choose the interpretation which is most likely to be fruitful in producing the best future physics. What I'm saying is, for the future physics, we don't know what that is yet. We want to get clearer on the interpretations of old theories first. And then we can see what's going to be useful later. So we're kind of looking at this intersection between old theories and new theories and how to move forward. So with our sort of three principles that we're looking at, we've got very good theoretical reasons for taking causal locality seriously, which is to satisfy the constraints of special relativity. There are good pragmatic reasons for taking gauge invariance seriously. So that's to ensure that changes in the values of the variables in our theory correspond to empirical differences that we can measure in the world. Separability, we're holding on to question. We've got these two different interpretations of the AB effect, one non-separable, one sort of meeting a formal criteria of separability. Do we need to maintain the principle of separability when we're doing physics in the future? So when we're learning about or developing theories for regimes where the physics is not yet settled, should we be bound to the principle of separability or not? So something that I've looked at in this context as a kind of foundation for quantum gravity again, I'm not going to go into too much detail about this. I'll try and draw out the kind of relevant features. One approach to quantum gravity, loop quantum gravity, attempts to solve the problem of time that arises in reparameterization invariant Hamiltonian mechanics. We've got Ravelli, Dittrich, and Thiemann. They develop gauge invariant observables, which are called complete observables. So just really quick kind of overview. If we have Hamiltonian mechanics, classical Hamiltonian mechanics, a lesson from general relativity is that physics ought to be time reparameterization invariant. We encode this in Hamiltonian mechanics, and then we get a difficulty with describing the dynamics of the basic variables that we start with. So one way of trying to solve that problem is to develop what's called a complete observable, or a set of complete observables. So just to go over what this is, little f and big T here, these are phase space functions. Y is a phase space point. Alpha TC is the Hamiltonian flow with respect to constraint C. And tau is a particular value, a specified value of one of our phase space functions. So we call the phase space functions, these ones, we call them partial observables. So they're just functions applied directly to your phase space points. They have gauge freedom in a reparameterization invariant theory. Okay, so they're not uniquely defined. So this object is gauge invariant, and it involves combining them. So our basic observable for this approach to loop quantum gravity is gauge invariant, but it has a kind of non-separability in the sense that it's a relation between distinct points of phase space. They can be represented in a sort of more abstract kind of space. And then we can make the ontology of complete observables separable with respect to that highly abstract space. But again, we can question the motivation for doing so, given that separability started off as being this practical requirement on doing experiments. So we've got this kind of tension then between, if we have the complete observable as being fundamental, it's non-separable, our ontology is non-separable. If we attribute physical reality to the partial observables, then we can restore separability. But what we have, the supervenience basis then is unphysical in the sense of containing gauge freedom. So Ravelli and Thiemann kind of comment on interpretations of this, or how to use this formalism. Thiemann attempts to reproduce the dynamics using only separable observables, but here separability is a formal mathematical requirement, which doesn't translate easily into the practical requirement on the experiments that we started with. So questioning here whether the principle of separability or some formalization of the principle of separability has become just habitual, or perhaps this is a question for Thiemann really, perhaps there are mathematical reasons for preferring separable observables in our ontology. In which case we can open up the question of separability again, but we're looking at, maybe we need a new word for it if it's just a formal mathematical requirement that can help us do the theoretical part. Ravelli, so Thiemann like attributes physical reality to only the complete observables and denies that the partial observables, that are the relata, he denies that they have any physical meaning because of their gauge dependence, and then tries to develop theories that use only separable complete observables. Ravelli goes down the other route and attributes some degree of physical reality to the partial observables, despite their gauge invariance. Gauge variance. So trying to kind of get clearer on Ravelli's interpretation, the way that we kind of understand this idea that we've got partial observables that have some degree of reality, but we can only do gauge invariant physics with them when we combine them. So we've got relations of the complete observables, relata of the partial observables that are being related. The way that we understand this can depend on whether a complete observable represents a relation between different fields interacting at the same point. So that would be something like the quantum field and the potential interacting at the same point. So we've got two different fields to find at the same point of physical space. That's one thing that we can use a complete observable to represent. Is that?
Yeah, so I'm just wondering what the same point means in the context of a general variant theory where I'm doing advantages. Or I know in Ravelli's formulation of equal gravity, then you replace the points by these sort of tetrahedra like quantum space-time. So I was wondering what I'm not sure. I was wondering what the same point meant in that context.
Yeah, it's kind of an open question, and it seems to depend on how we recover space-time. So the same point relevant for thinking about separability and the practical applicability of separability would be thinking about the same space-time point, or at least the same spatial point, which depends on how we recover space-time.
Okay, so you're talking about restore separability with respect to the classical limit in some sense?
Either with respect to the classical limit, or so we've got the interaction between two fields with respect to a third field representing space-time. That could be one way of thinking about it.
Yes.
That would help us to define
I
the
see.
same point.
Yes.
The complete observables themselves, the way that they're formalized, they're flexible with this. They can be used either, you can sort of think of them in that way, or you can think of them as they could model different parts of the same field at different locations. But yeah, which of these cases they're representing depends on how we recover space-time, or whether we're using a kind of background to do that.
Okay, so this is where you've got something to say here.
Yeah, this part is all a bit mysterious to me as well, so happy to talk more about it later. But yeah, the same point is ambiguous. But if we had some way, maybe depending on how we recover space-time, if we had some way of ensuring that a complete observable, or the physically real complete observables, are those which represent an interaction between different fields at the same point, then we can restore a practical sort of separability. So have we learned anything about the metaphysical thesis of separability, i.e. is the metaphysical or modal structure of the physical world separable? Have we learned anything, or nothing concrete, I guess? It's kind of, we would like the physical world to be separable enough that we can do meaningful experiments. So we've learned more about how much separability we want in order to be able to continue with physics. Okay, so we're not sort of abandoning the principle of separability altogether, but we're trying to get more clear on the practical requirement of separability and the metaphysical thesis of separability, and then mathematical formalizations of these. So we've been sort of using a methodology that's kind of in the spirit of the principle of naturalistic closure. So, for example, the insistence on cause and locality is motivated by the need to unify our preferred explanation of the AB effect or our preferred approach to quantum gravity with the constraints of special relativity. However, something else which comes out of this is that the principle of naturalistic closure might be guilty of conflating metaphysics with pragmatics. Guilty of conflating, that's one way of putting it, or we can say that we learn something about the relationships between metaphysics and pragmatics through this exercise. So maybe the sort of condensed version of the principle of naturalistic closure that I presented does conflate metaphysics with pragmatics. It involves metaphysical features when we're talking about explanation and modelling the structure of the physical world. It also involves pragmatics, saying that those metaphysical principles or ideas that we should take seriously are those that help with the production of future physics. But then we can connect them in the sense that whatever practical considerations, so metaphysical principles chosen for practical reasons, they only work if the world allows them to. Okay, so we've got kind of, in the case of the AB effect, we've got a clear situation where the world is kind of kicking back and saying maybe it's not separable in the way that we thought. So then we're trying to save the pragmatic principle whilst updating our metaphysical intuition. Okay. So part of this, so we mentioned something about intuition at the beginning, in everyday or habitual intuitions playing no role in the development of physics. A closer reading of the work of Ladyman and Ross suggests that rather than just abandoning all reference to intuition and just doing physics, and then when we want to do metaphysics, all we have to do is study maths and not think about the interpretation, not try and fit it with what we believe already. That's not quite what they wanted to say. It's more that the intuitions we start out with are not the intuitions that we end up with after studying some physics. And we ought not to be bound by our kind of habitual intuitions. So rather than abandoning all intuition, we want to let our intuitions be updated and revised in light of research in physics. So with the principle of separability, this is exactly what has happened. We're finding specific cases where separability or certain formal definitions of separability fail. But then I found somewhere that Einstein, when he was first writing about the principle of separability, he was very strong in his sort of advocating of it. But he says that it originates in common thought, which suggests to me that it's exactly the kind of intuition or conceptual principle that ought to be revised as physics progresses. So if we've got some principle going on in the background that's an intuition that's helping us to do physics, helping us to understand how to set up experiments and so on, we then sort of, as things develop, we find that those intuitions need to be revised. Okay. And then just to finish, I've just got a few kind of ways that everyday or habitual intuitions can actually play some role in physics. So we're kind of weakening this really negative view of intuition. So they can allow us to articulate what was once believed, what it is we are revising in light of physical evidence. So with respect to the principle of separability, we want to be clear on what Einstein thought about it, why he thought it was a good idea, why it's practically useful for doing experiments, and also what habitual or everyday intuitions it's drawing on. We want to be really clear on that. So then we can point exactly in the direction of what we need to change about our beliefs, about the metaphysical structure of the world, and what we need to keep the same as requirements for doing physics moving forward. So everyday intuitions can help us to understand the further implications of constraints on modal structure or on the metaphysical structure of the world. And it can also, we can use everyday or habitual intuitions to give characterizations of features of the manifest image so that they can be explained in scientific terms. So Ladyman and Ross were sort of fearful or grumpy about metaphysics going off too far in a direction away from physics and not making contact with physics. But perhaps then their really strong characterization of naturalized metaphysics allows physics to go too far away from the manifest image. So we end up with metaphysics being sort of some formal study of mathematics and physical theory and experimental situations, but without making any reference to our sort of natural human intuition. Perhaps we're no longer explaining anything and physics can go too far off in a different direction. So I want to try and connect features of the manifest image to features of scientific theory. So then we're approaching unity between the two. I've just got a few selected references that don't fit on the screen. There's more you can ask me. I can't remember how long we're going. That's all. Thanks very much for listening.